Welcome to Ganitika.com. This is a website for mathematics lovers, learners, and leaders. Today, let's see how to convert a complex number into its polar form. A complex number is usually written as a plus bi, and here are some examples of complex number which you should have already learned. So you can see that every complex number has two parts. The first part is called a real part and the second part is called the imaginary part. In the imaginary part, we have the imaginary number I, which is equal to square root of minus 1. We also know that a and b are real numbers. A or b could be 0. If a is 0, we get bi, which is a purely imaginary number, and if b is 0, we get a, which is a purely real number. And we already know all these things. So let's see how to represent a complex number in the Argand diagram. An Argand diagram has two axes, real and imaginary. It is similar to the coordinate axis that we usually do, x and y axis. In this case, x axis has real numbers while y axis has imaginary numbers. So for example, if you want to represent 3 plus 4i on this diagram, you will represent it as a point 3, 4 because 3 is the real part and 4 is the imaginary part. So the point 3, 4 on the Argand diagram represents the complex number 3 plus 4i. For example, minus 2 minus 3i is a point minus 2, minus 3 here, which is in the third quadrant. Therefore, this is the complex number minus 2 minus 3i on the Argand diagram. Try to represent the other two examples on the Argand diagram. Let's proceed further to know what is modulus of a complex number, because this is a base for converting complex number into polar form. So let's consider this complex number z equal to a plus bi, and you know that a and b are real numbers and I is square root of minus 1. Modulus of z is written as like this within two straight lines, like you write absolute values, and it is given by square root of a square plus b square. So considering the Argand diagram, a plus bi is a point a comma b on the Argand diagram, real and imaginary axis. And since a and b are coordinates of a point, this is b and this is a. Therefore, this is your complex number a plus bi. And using the Pythagoras theorem, the length of this red line would be square root of a square plus b square. Therefore, if I call these points as o and p, the modulus of z is nothing but the length of OP, which is equal to square root of a square plus b square. Therefore, if p represents any complex number on the Argand diagram, the distance of p from the origin is given by the modulus of the complex number. Consider this example 3 plus 4i and find the modulus of this, which gives you 5. So this point z 3, 4 is here, and this is the complex number with modulus 5, which means its distance from the origin is 5 units, which also means that it is on the circumference of a circle of radius 5 units. In the same way, if you consider this example 3 minus 4i, the modulus of 3 minus 4i is also equal to 5, which means it's somewhere on the circumference of the same circle, right? But 3 minus 4i is the point 3, minus 4, which is here. And this is on the circumference of the same circle with 5 units. Similarly, minus 3 plus 4i is the point minus 3, 4, which is on this side of the circle. And minus 3 minus 4i is on this side of the circle, which means you have 3 plus 4i on the first quadrant, minus 3 plus 4i on the second quadrant, minus 3 minus 4i on the third quadrant, and 3 minus 4i on the fourth quadrant, all of them placed over the circumference of the same circle of 5 units, which is the modulus of all these complex numbers. Let's consider what is argument of a complex number. This is also important to convert a complex number into its polar form. Consider this z as a plus bi. This complex number can be represented on an Argand diagram like this. If you consider the positive real axis as 0 degrees, the angle from 0 degrees to the complex number is given as the argument of z. In this case, it's equal to theta, and from the right angle triangle that you have on the diagram, we have theta is equal to tan inverse of b over a, because b is the opposite side and a is the adjacent side to theta. So let's consider an example z equal to square root of 3 plus I. This gives you the argument of z as tan inverse of 1 over square root of 3, because 1 is b and square root of 3 is a. So according to the formula we had, argument of z is tan inverse of b over a. In this case, 1 over square root of 3. We know that tan inverse of 1 over root 3 is pi over 6 in radians or 30 degrees. Therefore, the complex number can be represented like this on the diagram, where this is square root of 3 plus I, which is the coordinate square root of 3 comma 1, and 30 degrees is the argument. Therefore, the complex number is placed at 30 degrees from the positive real axis. Consider the example square root of 3 minus I. This means argument of z equal to tan inverse of negative 1 over root 3, which gives you negative pi over 6, and it is in the fourth quadrant because the coordinate is square root of 3 comma minus 1. Therefore, the argument we have here is tan inverse of minus 1 over square root of 3, which gives you negative pi over 6 or negative 30, which is measured from 0 degrees clockwise. So this is negative 30 degrees because it is in the fourth quadrant. We have the argument of z as negative 30 degrees. Consider this example, negative square root of 3 plus I. The argument of z for this is tan inverse of 1 over negative square root of 3, which is actually equal to tan inverse of negative 1 over square root of 3. You will be tempted to write this as negative 30 degrees as before, but you can see that the coordinates are negative root 3 comma 1. So which quadrant it is in? Negative root 3 comma 1 is in the second quadrant. Therefore, negative 30 degrees is not the answer for the argument for this question. So we need to consider this as being in the second quadrant. This is 30 degrees. Therefore, the argument of z is measured from the 0 degrees up to the complex number, which is here. Therefore, the argument of this complex number is pi minus pi over 6 or 180 minus 30, which is 150 degrees. Therefore, you have to consider where the complex number is situated. In this case, it is situated in the second quadrant. Therefore, tan inverse of 1 over negative root 3 is not the same as minus 30 degrees. It is same as 150 degrees. Consider this example, minus square root of 3 minus I. And the argument of z looks like tan inverse of minus 1 over minus root 3, which is same as tan inverse of 1 over root 3, and you will be tempted to write this as positive 30 degrees, which is not correct because this is not the complex number square root of 3 plus I. This is the complex number minus root 3 minus I, which is going to be in the quadrant here, minus square root of 3 minus 1, which is the third quadrant. And therefore, the argument is from the 0 degrees clockwise up to the complex number, right? Therefore, the black arrow which is shown clockwise from 0 degrees is the actual argument of this complex number. Therefore, argument of z is minus 5 pi over 6 or minus 150 degrees. Because it is measured clockwise from 0 degrees, it is a negative value. From these four examples, you can see that argument of any complex number can be only between negative pi to pi. And we include pi in this range. And we don't include minus pi in this range because minus pi and pi have the same position, which is on the left side of the real axis. Argument of a complex number is either 0 to minus pi or 0 to pi, depending upon which quadrant it is in. If it is in the first and second quadrant, the argument will be between 0 and pi. If it is in the third and fourth quadrant, the argument will be between 0 and minus pi. Let's come to the main point of this video, converting a complex number from Cartesian to polar form. A complex number of this form is called a Cartesian form, especially because a plus bi can be represented as a coordinate a comma b on real and imaginary axis. Because it is on a Cartesian plane, we call this as in Cartesian form. Once you have a plus bi, you can find the modulus of z and the argument of z, which gives you modulus z and theta. And if you write the complex number as modulus z into cos theta plus I sin theta, we say that the complex number is in polar form. Usually modulus z is written as r, which gives you the radius of the circle that this complex number is on. We have seen these things before, but the main point here is the polar form of any complex number is modulus of z times cos theta plus I sin theta, where theta is the argument of z. So if you have a complex number a plus bi as z, and you can find modulus z which is equal to r, and you can also find argument of z which is equal to theta, and once you find these two values r and theta, you can convert the complex number into polar form as like this: r times cos theta plus I sin theta In simpler form, this is written as r cis theta. You can see that in polar form, the complex number has two parameters, r and theta. We know that r is the radius of the circle on whose circumference the complex number is positioned, and theta is the angle from the 0 degrees up to the complex number. So this is where the complex number is, and its coordinates are r cos theta, r sin theta. So the coordinates of the complex number in polar form is given by r cos theta, r sin theta, which means the x value is r cos theta and the y value is r sin theta, which can be obtained from the right angle triangle that is shown here. So r cos theta, r sin theta is the coordinate when represented in polar form, whereas a, b is the coordinate when represented in Cartesian form for a complex number. Consider this complex number 2 plus I, and let's convert this into polar form. So we need to first find r and theta, which we have found here. Theta is tan inverse of 1 over 2. Since 2 plus I is in the first quadrant, we get the value of theta directly from tan inverse of half, which is 26.5 degrees approximately. Converting this to polar form, the polar form is, remember, r cis theta, therefore r is square root of 5, cis 26.5 degrees. This is the polar form for 2 plus I. Let's consider another example, minus 2 plus I. R is the same, square root of 5, but theta is 180 minus 26.5 because this is in the second quadrant, minus 2, 1. So you can see that this is in the second quadrant, therefore the angle is here, therefore it is 180 minus 26.5, which is 153.5 degrees. Therefore the polar form for this complex number minus 2 plus I is square root of 5 cis 153.5 degrees, cos 153.5 plus I sin 153.5. Consider another example, 2 minus I. In this case, r is the same, square root of 5, but theta is minus 26.5. Why? Because this is in the fourth quadrant, therefore your angle is taken on the clockwise direction from the 0 degrees. Therefore, the polar form is square root of 5 cis minus 26.5 degrees, which is also written as square root of 5 times cos minus 26.5 degrees plus I sin, I think I missed the I there, I sin minus 26.5 degrees. We know that cos minus theta is cos theta and sin minus theta is sin theta. Therefore, this can be represented as cos 26.5 degrees minus I sin 26.5 degrees. Therefore, you can see that r cis minus theta is nothing but r cos theta minus I sin theta. So, cos minus theta plus I sin minus theta becomes cos theta minus I sin theta. Try to convert minus 2i minus I into polar form now. Are you ready? The answer is square root of 5 cis minus 153.5 degrees because it is in the third quadrant, minus 2, minus 1. Therefore, it is on the negative side of the, it is on the third quadrant, which gives you negative value. Negative 153.5 degrees is the argument. I hope you understood and enjoyed this video. Thanks for watching. Bye-bye.